Right. So, Andrew, I think we are good to start. So, let me do the formal introduction. So, welcome to session 11 of the masterclass in audio. Today, we have with us, and we are extremely privileged and grateful to have with us a legendary figure in the field of audio, Andrew Jones. He needs no introduction to anyone who's been there in audio. He spent more than 5 decades in the field, and he's one of the most acknowledged and accomplished loudspeaker designers, among many other things. And he started at a very young age, and we are really happy to have Andrew today with us. So today, Andrew is going to be touching upon. I don't think I need to really talk about what Andrew has accomplished because he's been associated with so many loudspeaker companies and so many audio companies in the past. So I think everyone is aware of that. There's no point in me repeating it. And the poster also carries a brief bio of Andrew. It's a very brief bio, but that's in his own words. So without further ado, I'll straight head into the session. I have a few. Today, Andrew is incidentally going to be just sharing his perspective and his wisdom on the topic of loudspeakers in specific, and generally about some other topics in audio also. His wisdom over a span of 5 decades. So I just want to start off the session with a question which I had in mind. I'm sure this question has been posed to Andrew many times in the past, but at the cost of repetition, I'll just maybe pose it once again to him. So it goes like this: that the classical question which most of the people have as a customer, like you're faced with a budget of, let's say, about $10,000 USD. How would you allocate that budget in various aspects of the audio chain, right from the loudspeaker, the amplifier, DAC, and various other component cables, acoustic treatment. And I would probably like to pose this question in two parts. One is for maybe a home theater, home cinema kind of a solution, and one is for a listening room, a two-channel kind of a solution. If you find that the budget is low, you're free to Andrew, you're free to, like, say, scale up the budget to whatever you deem fit as a suitable budget to start off with. I was just looking at approximately $10,000 to $20,000 in that range.
I think it's budget independent to a degree, unless you're also including treating the room.
Yes.
But yeah, because with the systems and electronics and speakers, all sorts of price points. But rooms, it's not so easy to get low cost into the room treatment. The old adage used to be 60% to the speakers, 40% to everything else. And I was very happy with that because being a speaker designer, I'm happy everybody spend most of the money on the speakers. It depends on your belief system. There are people who believe that once an amplifier just measures reasonably good, then they're all essentially indistinguishable, and you can just purchase based on numbers. And there's a number of websites that do that, measurements, and then if it measures okay, that's all the money you need to spend. But in system building, clearly the item that has most impact, most differences in sound between different brands are the loudspeakers. And so it's very good to concentrate sufficient money on the speakers, as long as you don't skimp too much on the rest of the system. There's no good. Source is very important, obviously, and it's the old adage with computers: garbage in, garbage out. If the speakers get better and better and better, they're just showing the limitations of your system. So you still have to have a balancing act. Although when I launched all the ELAC products, because I was launching products at $250 US a pair, my first outing with them, I showed them with $4,000 of source electronics for a $250 speaker. And that was just to show you a different concept of balancing a system, that the speakers were such surprising value that you could put them on the end of $4,000 of electronics and get a really good sound. But there was also the other way of looking at it. I used to tell people, look, I'm just launching the ELAC product. You spend your money on, say you're buying a $5,000 system, spend most of it on electronics for now, spend $250 on my speaker. By the time you're ready to upgrade, I'll have my next more expensive speaker available to sell to you. And then you upgrade to that, you can keep the electronics. And the next time, just so every time I release a new product category, a new price, you just keep spending on my speakers. So it seemed a very wise business advice on my part. But nonetheless, you have to get things in balance. But you can't forget that a loudspeaker does not exist in isolation, in the sense that your source and the electronics, they have an input and an output. A speaker has an input and a multitude of outputs because it's radiating in all directions, and you can only hear a system when it's set up in a room. The only time we ever could listen to a speaker without a room is if it's an anechoic chamber. Now, I've done that plenty of times, and I went through a very interesting 2 to 3 year research project when I was at KEF of setting up a system in anechoic chamber and then simulating with additional speakers all the room reverberation you'd get. So you could investigate room acoustics. But if you turn all of that off and just listen to a pair of speakers in an anechoic chamber without any reflections, it sounds awful. We haven't balanced the speakers. We haven't recorded the music for that kind of playback presentation. And this is one of the problems when it comes to both designing speakers and setting them up. What is the room doing? You can't really think of a stereo system or a home theater system without thinking about the room it's going in. So as a speaker designer, you have to be aware of that. You have to know the impact of the room acoustics on the speaker. You have to have a good idea of where to place speakers in the room, how to treat them, and just what kind of room sound that you want. And the difficulty is that in isolation, like we were just discussing about my listening room, I've spent a lot of time thinking through how to treat the room in a way that it still feels like you're just in a nice living room, in a nice living space. And there's very little to point at to go, oh, I couldn't have that in my room. That's crazy acoustic treatment. You go into so many dealer demo rooms, or you go to shows. Shows are a different issue because you've got a day to take a stripped out hotel bedroom and try and make good sound in there. So definitely a very special case, but I think I've got rather good at doing it. But that's the case, those two cases where they've taken these square panels, or rectangular 2 foot by 4 foot panels, which are either diffusers or absorbers, and just stuck them on the wall at certain reflection points and called it room treatment. And it neither works well enough, nor does it look like anything you'd be allowed to have in your house. And so it's important to be thinking in terms of what kind of things in a room help rather than hinder. And I like to look at on all these various chat rooms and Facebook stuff of people's systems, because they photograph their systems in the room. And it gives you a good perspective of what people are actually doing, either through ignorance or from lack of availability to place the system any better. And it gives you, it sort of humbles you to think, oh, I'm spending all the time designing these speakers and trying to show them in a perfect way. And yet,
Right.
for a lot of people, they can't recreate that. But my job, there's 2 parts of how I go about designing the speaker. Obviously, I'm always trying to give great value, but I'm always trying to in that great value, I want you to think that, oh, I know people said they were good. I didn't realize they were this good. So I want it to surprise you, but I also want to be aware of whenever I can show you the full capability of what that speaker or the electronics I associate with it can do. I don't want to set up a demo in a hotel room and do nothing to the room and say, well, this is what you get if your room hasn't had any treatment. I can see some value to that, like I'm presenting a realistic situation. Yeah. But then what I'm doing is dooming you to never knowing what that piece of equipment can sound like if you ever got the opportunity to do something. And like I say, some rooms are set up due to ignorance. People don't understand just how much impact a room has had. Some shows, they've set up identical systems linked together in adjacent rooms with adjoining doors. So you can be listening in one side and it's the same system, but in an untreated room. The other side is a treated room. Then you just run through the door, catch up with the music, and you go, oh, that's different. And that's the only thing that changes the room. So it's important to be able to try and spend money on that. One of the problems is there's often a difficulty between home theatre requirements and stereo. Right. Home theatre tends to be mixed for a much deader acoustic because it's a surround sound system rather than just stereo. The surround field is recreated by the use of having all the surround speakers. And so in theatre situations, you're deliberately taking the room out of the equation to a larger extent than you would in a stereo system. In a stereo system, we've got a pair of speakers up front. So any feeling of being immersed in the sound is the reflections coming in the room. And I know that they are in addition to whatever was recorded into the music, but nonetheless, they are there and an important contributor to how the system sounds. So we let's say, listening to a stereo system in a dead acoustic is not such an enjoyable experience. And so we have to be aware of that.
Okay.
But in terms of giving a budget for how you split between the various components, it's a bit difficult to say that absolutely, because so many times we know if you're into the hobby, you're going to be upgrading. Right. And so are you thinking of a budget where this is the system, this is the only system I'm ever going to spend money on. Once I've got this, I'm done, I'll be happy. Yeah, audiophiles are never happy. Right. And so therefore, do I choose my starting budget as something that is the optimum for allowing me to upgrade? And that's why I said with the first ELAC demo, $4,000 in electronics gives you the chance, the component that's gonna give most impact ultimately as you upgrade is the speaker. And so this gives you the chance to, okay, I'm settled with the electronics now, just concentrate on the speakers.
So if I have to summarize this particular discussion in a nutshell, would I be right in saying that, assuming that the room is adequately treated or taken care of, you will allocate the maximum budget by and large to the loudspeaker? And of course, you will, of course, ensuring that the electronics are also adequately taken care of. It's not that you're going to be just looking at the loudspeaker alone. But the loudspeaker happens to be, as you said, the one element which has the maximum scope of upgradation and trying to get the maximum juice from your system. Is that right?
I think so. Yes. Yeah.
Okay. Okay. So moving on,
you won't spare any budget on cables?
Cables is not on my discussion list. You know, I'm not going to get into trouble with this. The influence of cables versus the cost. It's the poor choice in upgrading. You upgrade the cables last when you're happy with everything else, in my view. I play around with cables. I get lots of cables on loan from manufacturers, but particularly as a designer, if people ask me, well, what kind of cable do you use inside the speaker? I say, why does it matter? You're listening to the outside of the speaker. Listen to my result of how I blended all the parts in the speaker. But I could spend a few hundred or a couple of $1,000s on cable inside the speaker if I wanted to go to extremes. But my view as a speaker engineer is that give me that amount of money and I'll shock you with how good the drivers can be or the improvements in the cabinets. So I'm always going to chase that rather than spending money. It's different when you're not the designer. If you're just putting together a system, you are the system designer in the sense that you are choosing all your different components based on your ideas of what you want it to sound like. And therefore, if you personally find it worthwhile in any particular system, spending more money on the cables, then have at it. That's your choice, but it's not my choice.
Thanks, Andrew. Moving on, the next topic which I wanted to just touch upon is the choice of loudspeaker for specific applications. Now coming to the aspect of like choosing a loudspeaker topology. Let's say we have a choice between maybe a crossoverless or a single driver kind of configuration, a two-way, a three-way, and multiple ways. What would be the reason why you would choose a particular topology as opposed to something else? And could you throw some light on that?
Well, certainly if we go back to a single full range driver, there's no such thing as a single full range driver, right? You can't cover the full spectrum at decent sound levels from a single driver. I know there are so-called single full range drivers, and certain people like what those do, but they are always rolled off at the top, particularly off axis. They never have great power handling at the bottom. So they're not in that sense full range. So the minimum is to go to a two-way. And I've spent a lot of my time designing three-way systems. If you want to be able to produce loud low bass without mid-range modulation, you need a three-way system. It's surprising what you can do with a two-way. And it's funny we talk about this because my latest speaker, not only is it a two-way, it's a two-way concentric. And if you look up any of the videos I've talked about concentric drives before, I've always said I'd never do a two-way concentric, and now I have. But everything's a set of compromises. And so if you think about a two-way, at least you've got one driver dedicated to the bass and mid-range and the other to the tweeter. So you have a chance of, in some respect, getting better sound. But you come across numerous added difficulties when you do split the sound across two components in terms of spacing of the drivers causing interference effects, directivity patterns being different off axis. So how do you balance the on axis sound with the off axis? And just from a listening point of view, we can detect sound source height, because of the way our ears work. And so we can detect to some degree that the sound is now spread in the vertical direction because the harmonics are coming from the tweeter and some of the fundamentals from the woofer. So we face all these challenges when we go to a two-way. We also face the challenge of, well, what crossover frequency should we pick? How capable are the drivers out of band? And how good they have to be, how far beyond the crossover point such that they no longer present a problem. If the tweeter goes down too low, we end up potentially burning it out, certainly increasing its distortion, because most tweeters have got very limited excursion. And so if you don't filter them at least second order, then you will always be increasing the power and the displacement to the speaker, to the tweeter, as you go down in frequency. And so if you consider first order crossovers a good idea, you really have to be careful about engineering the tweeter to make sure that it's low distortion at the lower frequencies and adequate power handling. There's a whole host of things you have to consider when you do that. Otherwise, you'll make them worse or burn them out. So you got to consider the complexity of the crossover, the cost of the components, the power handling that you require. So you bring in all these extra design objectives when you go to a two-way, which you then multiply when you go to a three-way. So there's further potential benefits going to a three-way if you want good, really good bass extension and you want to play the bass loud. Because basically anytime the driver starts moving, then it's not moving as you intend, right? If you look at all the distortion mechanisms as a driver starts moving any significant distance, you'll see that not only do you see harmonic distortion coming in, but you'll get lots of types of intermodulation distortion.
Right.
And so the more bass you play, the more mid-range modulation. A good test, there's a London Grammar track that I use called Hey Now. And there's a female voice singing, and then at some point some really deep synthesizer notes come in. And they're typically below the tuning frequency of a lot of especially vented box loudspeakers. And you'll see the driver start to move quite a long way, even when it's not strongly reproducing, it's not big enough or enough movement to properly reproduce that low tone. But that low tone is soaking up the excursion of the driver, and you'll just hear the modulation on the vocal. It's very apparent. In a three-way system, that does not happen because the frequency ranges are separated. So you can do so much more when you go to a three-way, except you've added more cost, more complexity, and particularly with the capability most people have of measuring what they're designing, then when you're designing a three-way system, every error that exists in every different measuring process all comes into play when you're trying to match the top end of the bass driver into the bottom end of the mid bass. It's that region where you just don't really know what's actually happening. Right. And this is another big problem in designing speakers. So what I had to do in this speaker is, if I'm going to go to a two-way, and of course I've done a lot of two-way systems of very affordable price points, where there's not much you can do special in the design of the motor structure to linearize the driver, other than having a long coil in a short gap. And the longer the coil, in some respects, the more linear it is. But that's only one of many non-linearities that occur in a drive unit. And so I paid particular attention in the design of this concentric driver. If I've said to myself, I would never do a two-way concentric because of the limitations, then I'm going to have to go, well, so what were those limitations, and can I get around them? And so that's what I made sure I do. And so particularly looking at the design of the motor structure in order to reduce flux modulation distortions and all these other mechanisms. So yes, you can design very good two-way systems, but you're still limited in how loud and how low they will play. So a three-way or four-way, as I did with TAD, is the ultimate expression of how to get everything from a speaker, but the complexity just goes up and up and up.
Just to add to this point, Andrew, so is there any benefit in going any number of ways above the three-way? So there are many loudspeakers which have multiple ways above the traditional three-way. And so is there any significant benefit, or are we talking about a point like a point of diminishing returns in terms of just having to increase the number of ways beyond three in the classical sense?
Yeah, so I think typically the three-way covers most of what most of us can accommodate, unless you go to these ultra expensive systems where they typically get probably four-way, because if you got a really big system and you want really big impact, you really want a dedicated subwoofer range from the speaker.
Right.
And so there it's justified. But the idea of, well, I could add a super tweeter.
I was just coming to that. So
yeah,
that would be so what would be the frequency bands that you would talk about typically?
So I typically consider a tweeter working anywhere from, if we're talking about conventional tweeters as opposed to compression drivers, so conventional direct radiator tweeter, then I'd consider anywhere from, let's say, 1.5K crossover point. So the tweeter covers the range above that. And even to go down to 1.5K, you got to do some special things with the tweeter and the waveguide and whatever to get it to work well down at those low frequencies. Crossing over to a super tweeter, that's really fraught with problems because it'll never perfectly integrate. Crossing over at 10 or 20K, the wavelengths are so short, you just don't. It doesn't integrate. It just adds some semblance of energy if you think you can hear it at those very high frequencies. And in fact, it can mess up the top end of what you would have got from the tweeter if you hadn't added the super tweeter. So it'll certainly change it, but change is not always good. Change is often just different. So then we talk about in a two-way system, obviously the bass driver, most bass drivers up to about 8-inch are pretty good to go out to a crossover point about 1.5K. But if you're talking about higher crossover points where you haven't engineered the tweeter to play very low, then the bigger drivers start to struggle to get up, to have a smooth enough response beyond the crossover point, so that they're adequately attenuated. The out-of-band resonances of the cone are adequately attenuated at high frequencies. And even there, you have to be careful because we tend to think in linear terms when we're talking about driver and crossover response. And so the issue is that in a linear system, we've got the driver and a crossover. And if in theory, we could put the crossover in front of the driver. I'm thinking conceptually, we've got a chain of components. And it doesn't matter which way round we put them in a linear system, we'll get the same end result in terms of frequency response. So we could put the crossover theoretically in front rather than after the driver, and the driver plus crossover response would be the same. But of course, we're not dealing with linear systems, we're dealing with non-linear systems. And so if we think that we take a driver and it's got out-of-band cone resonances, some of those cone resonances are non-linear, so they add a bit of distortion themselves. But even beyond that, we filter the input signal at an adequate rate so that we don't excite those cone resonances. So let's say we cross over at 1.5K, first cone resonance is at 3K, but we've attenuated, let's say 20 dB by the time of 3K. Then we've suppressed that cone resonance by 20 dB. Yeah, we're all good. Except we're not, because the driver motor creates distortion. So now suppose we put in a 1K tone and it has third harmonic distortion. It's at 3K. The generation of that 3K tone has come after the filter. So it now directly excites that cone resonance. So just filtering off the input signal wasn't enough to take care of those out-of-band resonances. So we've got all those kind of things to consider when we look at characteristics of drivers. So in a two-way system, trying to get an 8-inch to perform really well up to a high enough frequency that we don't have to worry about it unless we've designed a really low distortion motor, then it becomes a bit difficult. That's why you'll see that most two-way systems are 5.25 or 6.5-inch bass drivers, with occasional use of 8-inch as long as we cross the tweeter over a bit lower to give us more safety band for the woofer, except of course we're stressing the tweeter more. So like I said, you have to take care of that. Everything's always a blend of compromises. I said over and over again that my job as a designer, I'm never going to make a perfect loudspeaker. All this talk about how should a speaker measure in order to inform you how it should sound. We'll never get, even if we agree that this is the perfect shape that the measured response should have. In any practical system, we're not going to fully get there. So we're talking about a compromised system, and what are the compromises I'm willing to accept, and what am I willing to reject or not try to take care of. So it's the art of blending those that determines ultimately what the speaker is going to sound like.
I always like to look at such problems as what they call in classical engineering terms as multi-constraint optimization, I think.
Absolutely. Yes. And so obviously the driver size sets a limit on what you can do with a two-way system. That's where you go to a three-way, and then the engineering exercises, well, what crossover frequency should I choose for the dedicated bass driver? Is it going to cross over 80 or 100 hertz, or 200 or 300 hertz? And there's a world of difference between those two. And I'll say the nice thing about designing with a two-way is these inaccuracy regions that you get when you're using different measurement techniques go away to some extent. It's definitely easier to do it with a two-way. And I remember designing the ELAC Cadante speaker, and it was something where the acoustic response, I had basically an acoustic filter on the output of the driver, so it was naturally band limited. But it was that roll-off was right in the region of maximum uncertainty in measurement techniques. And so it took me a long time to work out how to properly measure that, even to properly assess its relative sensitivity versus the mid-range driver and all this kind of stuff. I really made the expression made a rod for my own back in proposing that system.
Okay, Andrew, we have a question from the audience. So we have, in fact, a loudspeaker designer himself in the audience. Sandeep, you want to unmute yourself and ask the question? Be a bit quick, please, Sandeep. Sandeep, please unmute yourself.
Yeah. Hi, Andrew.
Hi there, how are you?
Hi, I'm fine. How are you? So, Andrew, I have a question. Consider it's a little bit of a deeper question. It's a multi-tier question. In the sense, like, see, I've seen one of your source point 10 speaker. So before that, let me introduce myself. We are a company called as Invention. We are based out of India, and we manufacture a lot of speakers, and we also manufacture amplifiers, stacks, preamps, and whatever. And we also started manufacturing our own drivers. And now the point which I was just looking at, because I mean we've been studying a lot about the the flux modulation. It's called the force factor modulation. Okay, now coming to the source point 10, like the way how we have designed the source point 10. So I've studied the white paper, what you have published, and I could see a couple of things in this. Is like, let me get to this question. It's a kind of multi-tier question, like I said. Usually what people end up doing is, people start to use the shorting rings to also called as the demodulation rings, as you know very well. Yeah. And the point, this is very interesting here, because whenever I see a concentric driver, I see that the tweeter has got a different magnet, and the mid bass or woofer gets a different magnet. They're not into the one single motor system. Right. So the point what I see is one of the biggest problems in the motor design, especially with the woofers, is that sorry, this question could be a little bit like 2-3 minutes, but it's a very interesting question. I would like to tell you. So what exactly is a problem is that whenever you go deeper in the frequencies, whenever you go quite deeper in the low frequencies, what happens is the kind of shorting ring, whatever that you are putting in, is not effective. It loses its effectiveness, and that's hence you get a lot of much higher voice coil inductance compared to a mid-range driver having a shorting ring, because the skin depth is kind of a lot basically when it comes to low frequency. Now coming to the source point 10, you have used something called as a twin drive, where the same motor structure is being the woofer magnet system is also used for the tweeter. So now coming to when you have this crescendos, when you have the complex orchestral playback, and you have a lot of low frequency and low mid to high frequency. Now the question comes here is that when it comes to unable to demodulate the low frequency, so this flux whatever gets into even the tweeter, because the tweeter is very sensitive, it even its microscopic displacements. So microscopic flux modulation, what you see in the with the tweeter as well. So this kind of demodulation. So my question is why it is not separated. I have seen the paper in which you have mentioned that the tweeter has got a flux density of 1.35 Tesla, which is a very good number, which is actually usually takes a large magnet to achieve that. Even for the tweeter. So my question is, have you observed the difference with like having a modulation happening with the tweeter because of the woofer, because they're sharing the same magnet system, the same motor. Yeah. So have you observed that? Because definitely there'll be a difference. I'm sure about that, because if you look at drivers like a field coils, where the magnetic field is extraordinarily stiff. But any of the permanent magnets would suffer from these kind of, somewhat softer, I wouldn't say as stiff as field coils, but at least you have some sort of softer demodulation. I'm very much concerned when especially when a tweeter is sharing a magnet system from the woofer, because this, if it is sharing from the mid-range, probably it would not have been a much problem. But when you are doing it with the woofer, which is going down to 45 hertz or 42, 40 hertz, now what's your take on it? Because as far as what I see, if you put a flux meter in the Gauss meter, which goes through the gap of the tweeter voice coil, and you start playing the woofer, you would definitely see a flux modulation happening inside the the tweeter gap. And what's your take on it? I'm just curious to know. How did you solve it, or how is it right now? Because that's surprising.
Thanks, Sandeep. Thanks. Yeah, please, Andrew. Go ahead.
There's a very quick answer to a long question. You think I'm going to tell you as a rival manufacturer? First of all, both gaps have got copper sleeves in. So I have, certainly in the tweeter and for the upper end of the mid-range, I have flux demodulation rings actually in the gap rather than outside the gap. But at the same time, certainly there's a lot of flux modulation cancellation because of the way the two magnets couple through to the base driver magnet gap, that they're in opposition as they drive the flux across the gap. So compared to what the coil is trying to do to demodulate. So everything the coil does to demodulate one magnet, it or to reduce the flux in one magnet, increases in the other. So those oppose each other and cancel out to quite a degree. So the actual result is lower distortion due to that magnet structure. And then some of the rest of it in the tweeter is taken care of with the flux demodulating ring. So there's a number of different approaches all added together to get that reduced modulation of the flux.
Okay.
Yeah, I have a smaller question, another small question, if you can do that. Maybe that would be quite interesting to know from a designer like you. One is, if you look at the magnetic top plate of a driver's top plate. Yes, because the magnet top plate and bottom plate. Yeah.
Oh, top plate.
Top plate. Okay. So now let's consider we have two cases. So we have one case with a constant BL factor of maybe 10 or whatever. So what if the thickness of the top plate is reduced to a considerable level to have a much higher flux density? For example, usually you observe about 0.8 to 1 Tesla. So what if we increase the flux density to a substantial level? We're talking about 1.3, 1.4 Tesla, but with reduced thickness so that the BL would be the same. So how would be the sound difference? What is your take on that?
Well, one thing you got to watch out for is that when you saturate the poles, that sounds like a good idea because you'll reduce flux modulation, but you can easily unsaturate them depending on the direction due to the flux from the coil itself. So although it looks saturated at higher powers, it isn't, and that can cause problems. So there's lots of different approaches you can use towards this. I tend to shy away from that situation of extreme flux density, just because that saturation issue, I'm not convinced that saturation is the way to go. Okay. And although the motor structures I'm looking at now, and the motor structures I did for all the TAD based drivers, I completely shied away from that approach because I went to short coil, to underhung designs. I had a 35mm long magnet gap with a 12m long coil for the 10-inch woofer, and that is by far a superior way of doing it. When you're moving towards the high end, there should be no justification in using overhung coils as opposed to underhung.
Correct. Andrew, just as a small point to check with you, that doesn't it affect the transient response? Because when you have the very loose and soft flux, or I don't say loose, at least to a level soft flux, wouldn't it get the transient response? Because you see, I mean, just as in case, couple of speakers with the underhung like ATCs or what you see in the market, so where they have most of the underhung designs, and you need a lot of power to get the output from that speaker, even though sensitivity is low, 86, 87 dB.
It depends how you do it. In the designs I'm doing, no, I've got lots of flux density in the gap because I'm doing other special magnet arrangements, so I get the advantages of both.
Makes sense. Yeah. Thank you, Andrew. Thanks a lot.
Yeah.
Thanks, Sandeep. Yeah. So moving on, the next point, which Andrew, I just wanted your let's say your inputs on that would be the choice of cabinet materials. So this is quite a wide topic that I think a lot of people have a lot of variety of opinions on this, and the choice of cabinet material, because I think the enclosure is a very, very important aspect of the loudspeaker. And so What's your experience and what does your what's your choice, like favorite choice of a material for the enclosure, and the reasons for the same?
Um, I wouldn't say I have a favorite choice of material. I see a lot of cabinets these days made of aluminum. Oh, I can say aluminium, can't I? I'm going to go back to aluminium. I had to spend 29 years saying aluminum. So when I look at aluminium cabinets, I see that they got as much or more bracing in them compared to wood. And so why is this material any superior? It needs even more bracing. Counterintuitive, that. So there's various aspects of what you're trying to do with a cabinet. And obviously, you got aspect of shape in order to control diffraction effects. You've got to control cabinet vibrations. And the cabinet has such a large surface area, way larger than the drive unit, that potentially it's a large radiator of sound, and obviously uncontrolled sound. How do you deal with that? What are the factors, especially in terms of what are the factors that excite, that put energy in the cabinet? You've got to think carefully about that, because our first thought is, oh, all the sound coming from the back of the driver is exciting the air inside the cabinet, which then pushes on the cabinet and excites the walls of the cabinet. But over a large frequency range, that's not what's exciting the cabinet maximally. The pressure inside the cabinet that's forcing the walls apart drops with higher frequencies. What stays constant is the acceleration force applied to the cabinet from the chassis and magnet assembly. Because if we think about it, just like with a gun, you've got recoil. The force is applied between the magnet and the coil. The coil goes one way, the magnet is pushed back the other. And the force is equal. The acceleration is in proportion to the masses. So if you think, let's say a 10-gram cone or moving mass and a 1 kilogram magnet and chassis system, then you'll get 1/100th of the acceleration, but equal force on the magnet. That has to go somewhere, and it ends up coupling into the cabinet. And so you get a mechanical reaction force excitation that then feeds the vibration modes in the cabinet. From a mechanical excitation point of view, and it resonates. So now we have to deal with that. And I published a paper once that ATC keeps republishing that talks about mechanical decoupling of the driver from the cabinet. We did this a lot at KEF with vibration mounts on the driver where you screwed it to the cabinet. BMW did that as well. I won't say KEF was the first to do it. It's an obvious idea, and I've done it in various ways through the years with different speakers. The problem is, and it can work if you, I don't know, especially guys who are building speakers. When you start screwing the driver into the chassis, and every time you kind of engage the screwdriver with the head of the screw, even if the screw isn't fully screwed down yet, but it's partially screwed into the cabinet, as you touch the head of the screw, you'll hear the cabinet. You can hear that bang amplified by the cabinet. And it makes you think, yeah, this is a very bad idea. This cabinet isn't working well enough. And in fact, one of the things that really made me aware of this at KEF, we had the impulse test chamber. We're obviously the pioneers of the impulse testing. And in those days, it was a true impulse that we were putting in. It wasn't a swept sine wave that is processed in order to calculate the impulse response. It was literally a pulse we put in of about 10 microseconds duration, etc. And so all you hear from the speaker is tick, 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 tick. And of course, it contains all frequencies all at the same time. And you do the Fourier transform, you get the frequency response.
Yep.
But the sound was clearly tick, 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 tick. Except since that was our universal test equipment, and we also had an anechoic chamber, we would also use the impulse response test system when we were measuring in the anechoic chamber. Well, if you're holding the speaker, as I typically did, I'd always have it connected and the tick, tick, tick going through. As I walked into the chamber, the speaker pointing away from me to put onto the stand. Once I'm inside the chamber, because of the directivity response of the speaker, I no longer hear all the higher frequency radiation. That's lost in the chamber. What I hear now is what the cabinet is doing. And that sound goes from a tick, tick, tick to a boing, boing, boing. You could literally hear the cabinet vibration modes.
Yeah.
And it made it very obvious, yeah, this cabinet needs treating, but it's very expensive to treat a cabinet. So how do you deal with it? If you do a listening test and a measurement test of taking that drive unit and rigidly bolting it to the cabinet, measuring cabinet vibration, and then just back off the screws, especially if you put rubber sleeves on the screws, so that they're not touching the driver, and the driver, you haven't fully squashed the gasket down yet. So you just back off that tension. It's surprising how much the sound of the cabinet reduces. Of course, now you've got a driver that's kind of flopping around.
So Andrew, I'm sorry to interrupt you. So did you have some prescriptions on the amount of tightening torque that you used to do, let's say while bolting your the driver to the cabinet? Like you all had some prescriptions?
Well, no, because it's.
So was it intuitive?
You need it tight for shipping and things like that.
Of course.
But if you back them off, unless you've done special treatment, what we did with Kef, we'd put a hard sleeve around the screw. Around that was the rubber washer that was attached to the chassis. So you could screw down as hard as you could, because you're screwing down onto this hard sleeve, inner sleeve within the rubber washer, so that you couldn't over compress anything. So tension on the screw head was just enough to secure it, kind of thing. Once it would bit down onto that sleeve, then everything else was floating and you were good to go. You didn't have to set a particular tension in to get the right amount of compression of the rubber washer. So you can use those kind of techniques. The problem is it's a first order, ultimately first order roll off, because the rubber washers are very lossy, because if you make a very low loss rubber, then at the resonant frequency the driver would start bouncing around. By the time you put enough loss factor in, you've essentially got a first order system at higher frequencies. And so the attenuation rate of that excitation force is very low compared to frequency. So it's difficult to get enough force reduction going into the cabinet. You can get a decent amount, but if you're trying to do, the secret would be to make it the resonant frequency of the driver on that compliance very low, so that it's starting to attenuate the transmission force at a low enough frequency, such that by the time you get to the cabinet resonant frequency, you've got a good amount of reduction. But then that means the driver is basically floppy, and people don't like the idea of their drivers flopping around. They think they should be rigidly attached, and a rigid cabinet and a rigid stand and spikes to the floor. All that spikes do is maximally couple it to the floor. They don't decouple. It's such a silly idea that spikes decouple. I mean, I don't know where people got that idea from. It doesn't take much measurement to show that's entirely wrong.
You're
So,
opening a Pandora's box. You're opening a Pandora's box.
yes, I
by
am. I
talking
know.
about-
And so, yeah, it's like a turntable, a
Yes.
suspended sub-chassis turntable. You set the resonant frequency down around 5 hertz or lower, but then it's going to bounce around. And so you put locking screws, for
True.
shipping. I think if I were to propose locking screws on a drive unit in a cabinet, everyone would think I was mad. Now in a three-way system, it's much easier because you can, just like with a driver, you try and get all the cone resonances above the crossover point. You could try and make the cabinet resonances above the operating range of the driver that's exciting the cabinet. So in a three-way system, suppose you cross over 100 something hertz and you got a cabinet resonance at 300, then you could conceivably, notwithstanding what I said before about distortion products and stuff, you could conceivably roll off the bass driver such that it never excited the cabinet. Now you've got to just deal with the mid-range driver. And so maybe you could attenuate it enough and make it floppy enough because you're not trying to use it in the range where it's flopping about, because you arrange that to be below the crossover point. You can try and do these kind of things, or you can put the mid-range in a separate enclosure that it itself is decoupled from everything else. And that's what I did with the original TAD Model 1. The concentric mid-range tweeter was in a cast head that just sat on top of the speaker. And so the bass cabinet was made rigid enough within its operating range, and the other cabinet had all sorts of, it's a cast cabinet made out of resin and aluminum with internal wood damping braces glued in and with driver decoupling. So I was doing everything to minimize those vibrations. So it is critical to the sound of a speaker to minimize those vibrations. It's just that it's very complex to do, especially in a manufacturing environment. Everybody wants to just take 4 or 6 screws and screw the driver into the box and we're done with. So otherwise, how do you build a box that's quiet enough? And it's not easy. People say, well, put enough bracing in. Well, bracing, it moves. You still got resonant modes. You've just moved them to a higher frequency. How high do you need to go before it's not too much of a problem? And because the cost of a box, the cabinet, is so high anyway compared to the cost of all the other components typically, it's expensive to do things with the box. So that is a problem. It's one I always think about, and it's something I always hear. I always know with a low-cost speaker, you're going to hear the cabinet. Yeah. And I've admitted it. The order of importance for me is drivers, crossover, cabinet in a low-cost system. Now, obviously, as you go to higher-end systems, you've got to pay more equal attention to everything and put them on the cabinet. And certainly with the source point 10s, yes, you can still hear the cabinet, but I've paid more attention. I've got thicker sidewalls and I've got more cross bracing, but not yet, because it's a two-way system, not yet decoupled the driver. I'm always thinking of schemes like that to fix the cabinet. But yeah, move away from a square box and a simple square box, and you're really increasing the cost of the system.
In fact, Andrew, the point also is that the materials obviously have an impact on the timbre of the loudspeaker, because ultimately I think the choice of the materials will also affect the timbre. So let's say maybe a metallic kind of a system, choice of aluminum might affect the timbre. It'll have a different kind of a signature with respect to, let's say, a material like wood, and of course different types of wood. And these days you have Some designers also using materials like concrete. So like, so it's quite an interesting mix of options that we end up having. So like, yeah.
Well, concrete's not a new concept. It's not got any better as a concept than the bad idea it was in the first place. Concrete's very resonant. You just have to tap a sheet of concrete, take a paving slab and hold it up. Not for long because it's too heavy to hold up for long, and just tap it and it rings like anything. So you got to do everything you would do. There's barely any materials that are not resonant and sometimes very high Q. So the other approach you can take is to damp them out. And you can do that with either mixing stuff into the material, rubber compounds or whatever. But unless you're casting a cabinet, any panel that has to be cut and bonded to make a cabinet, if you start putting constrained layer damping in, as you start cutting in, cutting through or V-grooving a constrained layer damped piece of material, true constrained layer that too rigid, outer and inner layer being rigid, and then the soft material in the middle, that plays havoc with your cutting tools and trying to keep it clean. So cabinet manufacturers really hate that idea. So you're always battling that with cabinets. Some of the best approaches are the ones that make it least manufacturable and hence put up the cost. Simple bracing, yes, it can help, but it's also moving those resonances into a different frequency range. So the timbre is changing not just due to the materials, but due to the construction.
The moving frequency, as you said, the moving of the frequency to different points.
Yeah.
Could you touch upon how you decouple drivers from the cabinet?
Sorry, say that again, please.
How do you decouple? You said one of the last things that you do in expensive speaker boxes is decoupling of the driver from the cabinet.
Yes. You mount it on compliant bushings. Just like with a car, you have springs between the wheel and the chassis, and then you have to damp that spring with the dampers in order to get the right characteristics. It's those kind of things you're doing, and it's just the kinds of materials you're using. The problem with like we did at KEF, the obvious way of damping it is at the point where you screw the chassis to the box. The problem is the center of mass of the driver. If the chassis plane, mounting plane is here, the center of mass is back here. So as soon as you put it on mounts, the driver's gonna try and flop like that until it meets some equilibrium with the tension in the rubber mounts. And so the driver's always going to be slightly tilted, and it moves more around in shipping. So then what you do sometimes, you put a rod out the back of the magnet through to some compliant mount in a wall or the back of the cabinet, and so you've spread the force points of where you're doing the isolation. But then that makes the construction more difficult because you got to be able to get screw it in from behind.
Right.
The fact that just from a practical point of view, if you just stop and think about it, and you think, okay, we've got this big heavy magnet, and we're going to mount it by the chassis right at the front plane. Why? Other than practicality, if that's where we can put the screws in from the inside, but shouldn't the mounting point be where the mass is? Shouldn't you have screw into the back of the magnet with an internal brace in the cabinet or something?
Correct. That's the way the pro guys do it, pro speakers, especially with the large compression drivers.
Yeah, because you kind of have to, because you got so much mass there, especially in drop tests. If you got a thin stamped steel chassis, you can twist the whole thing. I've had drop tests where my cast aluminum chassis have just shattered because of the force on the magnet. So it kind of seems perverse. I know. In reality, I know why we do it. It's easy, but
Convenience.
convenience, yes. So we've got that issue of cabinet vibration, but then of course we have diffraction, and particularly important with concentric drivers, because everything's symmetrical about a concentric driver. It's very difficult to put a whole concentric driver sufficiently off-center in the cabinet to try and ameliorate some of the effects of cabinet diffraction. So it's very sensitive to what the shape of the cabinet is for diffraction. So in a two-way system, we can offset the tweeter from the center line, but then you have to have a left hand and a right hand speaker, and then you'll get everyone arguing, well, should the tweeter be on the inside or should it be on the outside? And but that doesn't eliminate diffraction, it just changes it. So you're always trying to deal with that effect. And again, back to practicalities. What's the simplest shape to manufacture a cabinet? A rectangular box.
Yep.
What's the worst shape you can have for cabinet diffraction? A rectangular box. Anytime you add a curve, it's ka-ching, price goes up. And whether it's molded or machined, and if you're machining MDF, then you have to paint it, and painting, breaking through that surface structure of the MDF into the inner core, then you've got to fill it, and it's multiple layers of paint, and it all adds up. But it is an important aspect of design. But again, it's one of those things where you pick your poison as to what you can deal with at any particular price point. Now, concentric drivers, sorry, not concentric, putting a tweeter in a waveguide at least helps to a degree, because the wavefront size, because the tweeter is now behind the baffle surface, the wavefront is expanded in such a way and guided by the waveguide that some of those diffraction irregularities are reduced. So waveguides, I would never design a system without a waveguide on a tweeter. The idea of just plonking a 1-inch tweeter straight on the surface of the baffle is just not something I would do. I've been doing waveguides for 35 years or more. So that's your choice of materials is a combination of how stiff do you want. Typically stiffer materials have got higher Q resonances, so when they do resonate, they're more audible. There is some thinking that, well, because of the way music is and the tonality of music, if I put a resonance between two notes, it'll never get energized, which I think is wishful thinking in a way. But one of my ELAC speakers, I do remember a reviewer being particularly interested in finding what the resonant frequency of the cabinet was. And he hadn't noticed it too much with the music he had been playing, but once he realized that there might be a cabinet resonance there, he said, so I went looking to find it, and I found a piece of music where it just happened to hit the resonant frequency of the cabinet, and then it was, he said, it vibrated like a sex toy, was his comment in the review. So
Andrew, since you touched briefly upon the topic of waveguides and how you never design speakers without a waveguide, would you what do you have to say of today's designers all working towards planar waveguides that make a cylindrical wavefront instead of a spherical wavefront? I mean, is that something that you would do in your future designs? Or
actually, I'm not quite clear what you mean by that, because unless you're talking about what they're doing with line arrays for PA systems, where they're
Look,
trying
even in
to.
the home also,
but
right? A lot of them are making these extremely long, tall boxes, which go like about
Yeah,
eight,
yeah.
and then
So
multiple drivers in them
line
all.
arrays, we have to be careful when we talk about line arrays, what we mean. From a physics and acoustics point of view, a line array is infinitely long, right? Once a speaker is not infinitely long, it's not a true line source. It's still omni at a sufficiently low frequency. And so unless there's the old Acustat electrostatic speaker that was 8 foot tall, and it just fits in under the ceiling of the standard ceiling height, especially in American homes. And so if you had a wood floor and a hard ceiling, then it was essentially an infinite line source, because the images in the ceiling go on forever. Under those conditions, a line source is a true line source, and its response does not change with distance. But a practical line source does. Above a breakpoint, its response changes with listening distance quite dramatically. So the calling a few tweeters, I'm going to extremes there. Some people, I've got a line source speaker, and it's maybe a foot or 2 foot tall of drivers. That's not a line source. Unless you're only using it at a frequency above the breakpoint where it changes from omni to line source. And then you've now got a line source tweeter with a regular bass driver, and now you've got a big mismatch. Its frequency response changes with distance again. So yes, you can. It's not easy to change a spherical sound source into a line source with in a waveguide without having some issues. But since I've never been looking to do that, I've only ever concentrated on spherical based or oblate spheroids. I was doing oblate spheroids before the term was coined, and developing my way of calculating mathematics, relatively straightforward mathematics. I am not a mathematician. I'll say that right now. I've always used the joke, a physicist is a failed mathematician, an engineer is a failed physicist, and I've worked my way down to engineer. So if the maths gets too complicated, I give that to someone else.
But then, Andrew, then that means you would never work with ribbons or with AMTs and stuff?
So I've worked with AMTs once.
Okay.
Not a big fan of them, but because I was with ELAC, I needed to make one speaker with AMTs. There's lots of problems with AMTs. And the idea that this concept that an AMT gives a 5 times multiplication of air velocity, that's just nonsense. All practical AMTs give nothing of the sort. And they're so full of resonances. It's not something I like the concept of. But and especially these days, so many even soft dome tweeters go out to 35, 40K that there's no reason to think that, I need an AMT because they go out to ultrasonic frequencies. My soft domes that I'm working with now and that I was working with ELAC went out as high as some of the AMTs that I looked at. So that's not a reason that an AMT is superior either. And AMTs just don't go down very well at low frequencies. So they're too troubled for me. I prefer a good design of soft dome or the right kind of hard dome, but that gets into difficult materials and engineering to get those resonances out high enough. At least with TAD, I was able to use beryllium, and that works out as a a really good material, but very, very costly. And we were using manufacturing technique that was vapor deposition rather than foil. So that was, in some regards, superior to foil, except it was very fragile. So that was a big downside, especially in compression drivers. If you drove those compression drivers too loud, you just hit the phase plug and it would just boom. There was one story, someone was setting up a big concert and it was all TAD compression drivers in all the PA systems, and some probably inexperienced, should we say, engineer managed to do something and he blew out every single driver. And this was like a few hours before the concert was due to start. And it's not like people stock a lot of those TAD compression drivers because they were obscenely expensive, or even sufficient diaphragm replacement kits. So they were phoning every studio throughout the country. Can you courier us? We promise we'll replace them, but if you've got any spare diaphragms, I think they needed something like 30 of them, something crazy.
Wow.
But they got back online. I'm not sure that guy was ever allowed in the system again.
Touch the button on the desk.
Yeah, do not touch this. In fact, even Air Studios, George Martin's studio, their mastering room is fitted out with TAD speakers, and they were always blowing them up. Not with music, but there was this patch panel going between mastering on a digital system versus an analog system, and there was this diagram of this patch panel saying, do not patch this way, because this way meant that you created a feedback loop and it would blow speakers. And even with that, I'd get calls, Andrew, we've blown up the speakers again, so-and-so patched the panel wrong. And I couldn't wait for the system to go through the parts department and send out replacements. I would just go to my lab and, do I still have a spare concentric driver? I just grab it and put it in a box and overnight it to England and then worry about getting my replacement after that. So I did that a few times. So we've sort of meandered off topic a bit because this came out of the cabinet diffraction.
Right.
I think it was waveguides, but yes, I've always been using waveguides and developed from a paper that was published in AES journal back in the 80s. I modified some of those mathematics to develop both spherical and oblate spheroidal waveguides, and you can get remarkable results when you put a tweeter in a good waveguide.
Andrew, I just want to draw your attention. So, Khushru, if you can unmute yourself and ask your question, please. Khushru, are you there?
Hello.
Yeah, Khushru, please ask.
Hi, Andrew.
Hi.
Hi. I have a very important, I won't say important, but a question which has always, a topic that has always intrigued me about concentric drivers.
Yes.
So, in a concentric driver, I love all of it except one part, which obviously you have solved, but at a higher frequency, depending upon the diameter of the base cone, you end up getting a notch because of the reflection you get out of the surround.
Yes.
And obviously in KEF, they seem to have solved that.
Yes, they have.
Yes, they have. And if I look at the KEF, the way it is, it's probably something similar to what Harry F. Olsen did with his LC1s. With those, something similar. But how do you, without fins, without breasts, if I may use the word for Harry F. Olsen, they used to talk about that in a very, very, how do you, yeah, I mean, they used to call them paper breasts. All right, that's true. Okay. how do you solve the problem about the reflection that comes back from the surround system? Do you invert the surround? What is it?
So, you're absolutely right. Like I said, with concentric drivers with diffraction, we're talking about diffraction effects.
Yes, you are.
But you got the point of maximum diffraction, whether it's a spherical waveguide or it's a concentric driver. Now, with the advantage with the spherical waveguide is you can make it perfectly smooth because it doesn't have to move. If it's a driver cone, it has to move. How do you allow it to move? So there's actually two things that affect the dip. One is the reflection from that outer edge, but the other is the transition into the, let's say, the throat of the waveguide.
Correct.
And that the dips you get at the high frequencies, which disappear off axis, are also dependent on how well you match it into that starting throat. And a couple of millimeters difference in how far the tweeter has to radiate before it reaches the expansion point can make a huge difference.
Yeah,
In terms of the surround, in terms of the surround, then clearly if the surround was flat, it wouldn't cause a diffraction. But then you'd have very, very limited movement of the cone. And so if you're doing it as a pure mid-range tweeter, then you can very readily reduce the diffraction effect at the edge, because you can have a very narrow surround, you can have a very low height surround, but as soon as you want it to move, you've got to deal with the surround. Now, obviously, you can see the way I did it with the source point is a corrugated surround.
You have a corrugated surround.
What I did first, I built a perfect waveguide, optimized it, the shapes for this tweeter, and then I cut a groove in there, and then I could drop in different shapes of surround into this waveguide and assess its behavior. And obviously choosing a corrugated one is sort of the best you can do, almost, as long as the corrugations are not too deep. It causes some effect, but not too gross. You know, it's still there. The other way.
Sorry to interrupt, but does it shift with the corrugated sound? Does it help you shift it from, let's say, like 7 to 8 kilohertz, where usually this problem takes place, to maybe about 10 to 11 kilohertz, where it doesn't matter so much?
No,
it frequency, or it remains within that 7 to 8 kilohertz range?
It always it depends on simply the diameter of that surround. It's a delay problem. You know, it re-radiates after a certain delay, having got to the edge of the cone, and then meets with the direct sound. So bigger drivers, to some degree, you could hope that the bigger the driver, the wavelength is larger, and so the perturbations due to the surround have less effect. So the dip might not be quite so pronounced. Whereas if you're doing a 4-inch driver, yes, it's moved it up in frequency, but made it deeper. But maybe do you care if it's a deep but narrow notch? There's all these kind of things you have to consider. And also the fact that it only happens on axis. Once you're about 10 degrees off axis, deep notch starts to go away. So we always used to say with KEF, because of the superior off-axis performance of a concentric versus a spaced two-way system, would you like it right in only one direction and wrong everywhere else? Or would you like it wrong in one specific direction and correct everywhere else? And that one specific direction is dead on axis. So as long as you listen 10 degrees off axis, you're good. And most people don't, I always say with any speaker, don't orient it to point directly at the listener. Just point it away, either cross it in front or behind you, and then you've solved that problem. But you've got good room sound, back to rooms, that directivity is important, and the concentric driver sort of is that best solution to it. So what KEF have done is they've got a flat-ish surround with certain features embossed into it, because the flatter you make the surround, the more surround resonances that you get.
Correct.
So they've got a combination treatment, and it works very well, combined with the fact that they've got that tulip whatever they call it, waveguide. They've
Correct.
put, it's a, one reason I don't often use metal domes especially in concentric drivers is it's very difficult to get rid of the dip. It just the way it is.
It is.
And they, all the KEF guys, Jack Ockley Brown and his team, I'm friends with that Jack, and we're always commenting on the forums together and teaching people. But I've always said that if you want to see the best measuring concentric driver, it's the ones that KEF are doing now.
Yes.
But he's got a team of people, all with PhDs, it seems, and they know how to
Yeah,
use all
he's
these
very young to have a PhD on himself.
Yeah, all these advanced modeling techniques, which I can't afford or don't know, have the time to learn. So I do it more through experimentation. But through a combination of techniques, they've eliminated that issue. Now, the problem with that surround that they use is you got very limited excursion capability. If you don't have much curvature, whether it's multiple wiggles or it's a single half roll, the less the disruption in the wavefront, the less the displacement you got from the driver. So it's severely excursion limited. Now that, getting back to problems with concentric drivers, that's not necessarily a bad idea, except that it means it can't play loud, low bass. And that's the reason why I felt going to the Source Point 10, once we'd got this idea of, Source Point, not Source Point at that point, a speaker, my first speaker from MoFi, we're going to do a big speaker, big box, because they're popular right now with the JBL L100 reissues and that kind of 70s look. If I got a big cone, it doesn't have to move so far. So that solves one of my issues, and then I can make a surround that doesn't have to move so far. So instead of doing 4 and 5 inch drivers, doing a 10 inch, I've got 4 times the area. So a quarter of the movement. So that really helps me. But yes, those, I've got some dips, but they're not nearly as bad as some of the other drivers I've designed. And it's always the case that as you're experimenting and you're building these perfect waveguides and whatever, you go, this is going to be a really good concentric driver because I've optimized the shape, and as long as the cone matches that and whatever, once you've finished building it as a driver and in a cabinet, you go, God, never as good as that first experimental one I built. And so you're always thinking, Mark II, maybe the reason engineers bring out Mark II versions of a speaker is all the things they didn't solve or ran out of time to solve in the Mark I. And you already know by production time what you're going to be doing in the Mark II. You just ran out of time to do it.
Okay. Interesting. So I just have another a brief, because you are doing concentric drivers and stuff like that. Okay.
Yeah.
I grew up with the speaker, so I'm just asking out of interest, because in modern context, how relevant would something like a classic monitor gold, what you had?
The tannoy monitor,
in a horn-loaded corner, horn-loaded cabinet.
Yeah, there's all sorts of things I can experiment with now. And bringing up the monitor gold, the tannoy, obviously when KEF did the first concentric driver, it wasn't that there were no concentric drivers prior to that. It's not we invented concentric drivers. We invented a different way of constructing them or developed because of the availability of neo magnets. You couldn't shrink a tweeter small enough to stick on the end of the woofer pole prior to neo magnets. So tannoy did it a different way, obviously with a compression driver mounted behind, but now it has to fire all the way through the pole. So that unusually, a tannoy driver or a dual concentric of that construction, the tweeter is delayed with respect to the sound from the woofer. Normally it's the other way round.
Other way around.
But although that can be easier to deal with if you want to add delay to the woofer to bring it back in alignment. But nonetheless, it's the opposite way around. So the advantage that Tannoy have got is that they're using all fine acoustics now, is that they're using a compression driver. And compression driver tweeter can play much lower than a typical dome tweeter. So you can push the crossover point lower. And so whereas 10-inch is the biggest cone I thought I wanted to try for this, because of if I'm using a regular tweeter and maybe I can push it down to 1.5K, I can maybe get the cone resonances up to about 3K-ish. And with a good motor structure, that helps me. But I wouldn't trying to do to 12 or 15-inch like Tannoy can do. I'm not sure I could do that with a regular tweeter.
Yes.
So, and the other reason for not using compression driver is I didn't want to seem to be too close to the concepts of what Tannoy have been doing. And I don't know how to design compression drivers.
Okay.
I've never designed a compression driver.
I agree. It's a completely different art from designing.
Yes, it is.
Direct
Yes.
irradiators. Just getting the phase plug is a science on its own.
Absolutely. Yes.
Yeah. And minimizing throat distortion is a rocket science of its own. I agree with that.
Yeah.
Great. I mean, thank you for answering that surround question, because that's something that, it's always, most people don't realize what happens in a dual concentric. And your response was fantastic. It's a corrugated surround, which really minimizes a lot of the problems.
Actually,
Thank you.
If you've looked at what, God, the company's just gone out of my mind. The Danish company that's Purify. Yeah, I was chatting to them at the Munich show. Again, I'm friends with Lars Risbo from Purify, and fantastic drivers. They're solving all the problems of drivers.
Insane drivers.
Of course, the price matches that. But
Insane.
I look at the surround and I'm thinking, yeah, you're never going to use that in a concentric driver.
Yeah.
Talk about maximizing diffraction from the surround. Oh, I see in the comments, someone said something about panzer holes for the cabinet control. Yeah, very expensive, very difficult to machine, but great material. Yes.
You will lose a set of diamond tools behind every pair that you make on panzer holes. You don't just throw them away.
So Andrew, just for your information, Khushru basically distributes the loudspeaker which uses panzer holes in India. So Kaiser Acoustics is a brand, and Khushru is the one who distributes that. Okay, I want to direct your question to your attention to one question, Andrew. So Abhishek is asking this question: what's the base reflex alignment?
Yes, I saw that.
Suggest? Yeah.
So this idea of particular alignments, either whether it's the crossover shape, is it a Butterworth, is it a Chebyshev, is it a Bessel, is it Linkwitz-Riley, and the same with the low end response. I don't worry about that at all. And the reason is those shapes only exist to make the mathematics simple in the days when Dick Small and Neville Teal were developing low frequency alignments. So you could do it on a calculator or a simple computer. It made the mathematics tenable and to chart and do everything. But they were always developed from a very simple equivalent circuit model of a loudspeaker. And that simple model ignored certain factors that exist in all drivers just to make the maths simple. Yeah. And the reality is, for most drivers, and particularly if you're thinking of bigger drivers for subwoofers and stuff, they've got so much voice coil inductance that the mathematics that go out the window.
It falls apart. And so I see people arguing about whether the Q should be 0.577 or 0.7 or stuff like that, and thinking it's not even that anyway. So we quickly moved on, Kef, from using that, and we developed
accurate equivalent circuit models of the loudspeaker. And so we predict the response from that. If you have the right equivalent circuit model and you measure driving unit impedance and optimize the model to that impedance curve, you can predict the near field response of the speaker to better than 0.5 dB accuracy. And I do this day in, day out. So once you do that, you never worry about tail small parameters again. And all that I need to know is the force factor, BL, mass, and area. That's, frequency response, or the resonant frequency, yes, I kind of need to know that. That's a secondary term. But those three are the primary drivers of what the low frequency response shape is. And so all I'll do is I'll take that equivalent circuit model, calculate what the frequency response is, and then play around with the circuit model and adjust it to a shape that looks about right. And I never worry whether it's QB3 or SB4 or SC4. It's such a minor thing. And of course, going back to driver nonlinearities, as soon as it starts moving, it no longer has that alignment. And in fact, Dick Small, I don't know if you realize, but Dick Small came to work with us at KEF. He came over on a 1-year sabbatical first, and then he ended up working full time with us. So he was technically my boss because I was in research. So he was made head of research and I worked with him. And we worked together on improving the equivalent circuit models of drivers to get more accuracy, and understood that, tail small parameters are just a simplified representation. It gets you in the ballpark, but don't fuss too much. And so one day he was giving a lecture at the Audio Engineering Society in London, and all of us guys went up to it, of course. And so one of our engineers actually asked a very good question. He said, so you call them the small signal parameters, and it's not because you are Dr. Small. What you mean is small signal parameters. And he said, what's the definition of small? And it was a very astute question. And Dick's answer was, pick a drive level, measure the parameters. Now double the drive level and half the drive level. If when you double the drive level, the parameters change, then your signal level is too high. If you halve it and they change, it was too low. It needs to be between those two limits, so that as you double or halve it, the answer is pretty much the same. Okay. And that was a very easy way to remember that. And yet, we know that if you take any drivers from any manufacturers and try and reproduce the test results that the manufacturer publishes of the tail small parameters, unless you do it in the same way they did, you can get different answers. And some of those tail small parameters are extremely sensitive to measurement level, and yet the final frequency response is not. And that's because we're concentrating on the wrong things. And so these endless discussions about the parameters are not ultimately of value. Build it and see, it gets you in the ballpark, as I say. But that's all we have to worry about.
Kushru, you have I think you have a point to add to this particular topic.
Yeah, I mean, you kind of answered it, because
exactly.
Tail small parameters are basically small signal parameters, and once you pump in, like, let's say 30-40 watts of power, like what they do in Pro Audio, then everything changes pretty dramatically in how the box behaves, how the driver behaves. And one of the things what people don't understand is, from a zero position where a driver is not moving, okay, and when you give it that impulse, the positive part of the driver moving forward and the negative part of the driver moving forward, what is the flux in the positive versus the negative in relationship, because that can vary dramatically, in many drivers, so you actually have a signal flux drop when it's moving backwards as compared to forward, and that you never realize and feel small.
Yeah,
Because then the driver
exactly.
The driver is doing something completely different from what your easy calculation on your scientific calculator does. You will never be able to predict that unless you have Kipel or some measurement like that, which will show you the stroke, and show you the distortion that you're going to go through in pluses, minus.
It's like when people talk about transient response of a base reflex versus a closed box, and they point to the mathematics and say one's a second order roll off, the other's fourth order, so the fourth order has a longer impulse response. You're almost never hearing that simple effect. What you're hearing is that it's easier as you start driving a base reflex for its tuning characteristics to change. So that's what you're hearing. It's not this theoretical second versus fourth order roll off.
And what most people don't realize is they talk about, transient response for base reflex versus a seal box. I have a simple thing to say. If the settling time is within 0.5 microseconds, you're not going to hear it anyway. Don't even get it. 0.5 milliseconds, you're not even going to hear it anyway. Because settling time is more important than whether it's a base reflex or whether it's supported. It's how fast the system settles as a whole. The group delay is all that matters in the end. If you're talking about timing.
Right. And as long as you get the low frequency, this is why the more extended the response, you can get that rising group delay out of the way, and then you're good. So extended response systems are better than band limited, but we know that. We always did know that.
Okay, Andrew, I think we have crossed about 90 minutes of your time, and while we would love to continue, I just leave it to you. Like, are you open for us to continue for some more time, or do we maybe defer this the next?
Just a few minutes more. We can always do another session some other time. I'm always happy to.
Awesome. So, is there any other question from the audience? If not, I can maybe pose some other question from my side. So, is there anyone else from the audience who wants to ask a question to Andrew? Okay. I wanted your inputs on maybe the genesis of the source point. Like, if you want to just talk about that a bit, how did you come to the source point, the 10 and the 8? That from all these loudspeaker designs that you have come up with over the years, over the decades rather.
The initial request was very simplified. This idea of big boxes for a change is in, so we get the chance to do a big bass driver to keep good bass. That was one directive. Can you do that? I thought that'll be fun to experiment with. I've done big bass drivers obviously with the TAD systems, but never since that. And so, this will be. I want to learn. I want to have fun experimenting and coming up with ideas. So the chance to work on something that I haven't really done before is always exciting. And so, work with big bass drivers. And since I always like to work with concentric drivers where I can, and like I've always said in the past, three-way systems for a concentric, it just got me thinking. So now I'm going to have a 10-inch bass driver and a concentric driver. Well, if it's a big bass driver, what size should be the concentric driver? And should it be a bigger one? Well, now I'm just kind of adding cost and cost and cost. And, whenever you're designing something, cost is obviously a constraint. Just from a point of view, where you're going to sell it, how many you're going to make, so which market are you aiming at for this? And are we taking out of the market that we were initially targeting? It doesn't preclude me from sometime doing a reference class system again. I have ideas of what I want to pursue for that. But there was a cost constraint of, if you could do something in this price range. So that was going to take it outside of that. And so that's when I thought, okay, well, 10-inch, what if that was a concentric driver? I've never been able to work on a 10-inch concentric driver, never thought I would. But if the area is big enough, maybe I can change my stance on never doing a two-way concentric, because the movement most of the time is much less, way less than I'd get from a 4.5 inch concentric or 5 inch concentric. And so that was the genesis of it. Oh, I could try doing a 10-inch concentric. So that drove the whole project. Once that idea was in my mind, start experimenting. What do I need to do to make a good 10-inch cone? It's got to go up to the mid-range. I've got to find a 10-inch driver design that will work well up to the lowest, beyond the lowest frequency at which I can comfortably take the tweeter. And so that was all the experimentation I was doing. How do I make it sound good as a 10-inch two-way? How do I design the tweeter to go down low enough? At least I'm helped by the fact that it's in a really big waveguide, so that reinforcement from the waveguide is working down to a much lower frequency, so that helps me extend the low frequency performance of the tweeter. But can I find an example of a 10-inch cone that works up to a high enough frequency? It's not commonly done these days in home audio. And so at least by if I can find just one cone that works up to a high enough frequency, then I know it can be done. Right. So I thought, well, pro audio is a better way or more likely to be using 10-inch cones as base mid-ranges. Now, of course, the requirements of performance for pro drivers is different from home audio, so it's not guaranteed I'll find one there, but at least there's a lot more examples to look at. And I went looking through all the catalogs of different drivers and found one, I think it was an Italian one, that went smoothly up to just above 3K, and I thought, it can be done. And out of all the material choices, that one happened to be a paper-based cone.
Wow.
So I'm doing a retro speaker in some respects for big woofers and big cabinets and style-wise, but not deliberately going to retro materials for the cone. It's just when you start looking at cone materials and what their capabilities are and their costs, paper in this instance can work very, very well. You don't have to just have all the latest, most exotic materials. Obviously, if you think you wouldn't obviously do a 10-inch beryllium driver, you couldn't either manufacture it or afford to manufacture it. And then you look at aluminum, doesn't really work that well as a 10-inch to go up to 3K. Again, Purify, their latest 10-inch driver, is really good. It goes very smooth up to 2K, but then it's got the right shape of dust cap on it to help control the cone motion. Well, I can't have a dust cap because it's a concentric driver. I'm reliant on totally the cone shape giving me the right performance. And so you keep going through all the characteristics of the exotic materials and realizing, they at this size, they're not going to work. They're not either not well enough damped, or formable, or whatever the reasons are. And I found that paper worked, so that's what I ended up using.
Great choice.
Yeah.
Any other questions from the audience? Thanks, Andrew, for that reply. Any other questions from the audience?
I just have one audiophile to audiophile question. Since Andrew worked in TAD, did you ever get to hear the big TAD studio monitor using dual 15 inches with that 4001 compression or 2001 compression driver designed by Shoujo Kinoshita?
Yep, definitely. Very good system. I often think, should I do something like that with put this 10-inch driver in with a couple of big bass drivers and see what I get. But yes, remarkable system.
That was a remarkable system.
Yeah.
Okay, thank you. Because I plan to experience it once in my life, which I haven't got a chance to do. And I've heard a lot. I've heard all over the world. But this is the one thing that eludes me.
Right.
So I thought I should ask an experienced engineer, designer, audiophile. Is
Yeah.
it worth the trip to Tokyo? That's all I wanted to ask.
Well, Tokyo is also an incredible place to go to. So yes,
Yeah.
definitely.
Thank you.
All right.
Right. So, Andrew, I think if there aren't any further questions, we will wrap up this session. Of course,
Okay.
there are some questions there are a pile of questions from my side, but I think we won't have sufficient time to cover them today. So I look forward to having you at a later date to cover up some more topics, and it's been a great time in covering the topics that we have done today. So without taking much more
I
of
would
your
just
time,
say one thing. I was being a bit cagey with some of the details what I've done with the magnet system when Sandeep was asking, just because, I can't give
I
away every
understand.
secret I've got. But
Of course, of course,
but
of
sorry,
course. But yeah,
Sandeep.
that's fine. That I think the basic idea was conveyed, and I think that we thank you for that.
Yeah.
So without taking much of your time, Andrew, thanks a lot for sharing your wisdom with us. It's been a great couple of hours that we have spent, and we have just completely lost track of the time. We have almost spent 2 hours right now, and that's the way it works. These topics are so interesting that once you expound on your wisdom, we just lose track of the time, and that's how it generally goes for any such a session.
Yeah.
Thanks a lot once again, Andrew, and have a great day, and see you soon at a future session. Thanks, guys, for your time, and I'm signing off. Good night. Good night.
All right. Good night.
Thank you.
Bye-bye.
Good day. Good day, Andrew.